This is an example of how to solve a problem using Gauss's law. So what we have in this case is a long cylinder with radius big R, and we're asked to determine the electric field at point P, which is a distance r over 2 from the center of the rod. We are told that at position P that the electric field is radially outward. So we have an electric field here that points radially outward. Now note that this is only going to work because we're in the center of the rod. If we were near the ends of this rod, we wouldn't have this electric field pointing radially outward. But since we're in the middle, we're okay. Okay, so our electric field points radially outward, and for part A, we're asked to draw the Gaussian surface that we're going to use to find the electric field. So for a Gaussian surface to be used for this, what we want are cases where the electric field pierces our Gaussian surface either parallel to the surface or perpendicular to the surface. And so the symmetry that we have here is one that works well with a cylinder. So we're going to use a cylinder of radius r over 2 as our Gaussian surface. Okay, so it has a radius of r over 2 and it has a length of L. So part B, what we're going to do is now use Gauss's law. So the first thing that we need to do is write down Gauss's law. Gauss's law says that the electric flux through a closed surface is equal to the enclosed charge divided by epsilon naught. And we can now evaluate this. Let's start with the left-hand side. So our electric flux through our Gaussian surface here, which is the cylinder, is going to be the flux through the top of that cylinder plus the flux through the bottom of that cylinder plus the flux through the side of that cylinder. Okay, so let's look at the top to start. At the top here, our area vector A points upward, whereas our electric field points radially outward. So E dot A is going to give us an electric flux of 0. That dot product comes into play. So for the top, we wind up getting an electric flux of 0. And likewise, we wind up getting the same thing for the bottom, an electric flux of 0. Now for the sides, the area vector for the sides is going to also point radially outward, so it points parallel to the electric field. And the electric field has the same magnitude everywhere on that outside of our Gaussian cylinder, and so we can write this as just being the strength of the electric field at a distance r over 2 from the center of the rod, and we're going to multiply that by the area of the side of our Gaussian cylinder. Okay. So that means that in total, this is going to wind up being E times the area for the side of our cylinder, which is the circumference of the cylinder, 2 times pi times r over 2, times the length of the cylinder. Okay, now we can move on and evaluate the right-hand side of this equation and look at the enclosed charge. Well, the enclosed charge is just going to be rho, the charge per unit volume, times the volume of our Gaussian surface. And that's just going to be rho times the volume of our cylinder. And the volume of a cylinder is pi times the radius of the cylinder, which in this case is big R over 2 squared, times L. And now we just combine these two together. So we have E times 2 pi R over 2 times L is equal to rho times pi times r over 2 squared times L. We get a lot of nice cancellations here. Pi's cancel. And we wind up getting a magnitude for the electric field of pi rho times r over 4 epsilon naught. That is our final answer.